Dear students, in physics, let's see another experiment now. This is about the determination of velocity of sound using a closed resonance tube and a tuning fork, and also determination of the end correction of the tube, right. So, here we have only one tuning fork and a closed resonance tube. Let me explain what we are going to do here. How do we get a closed resonance tube and all? See, if you get a resonance tube, okay, one side closed, we take a tuning fork, vibrate it and keep it close to the opening of this resonance tube. This is one side closed resonance tube. So, the air particles, air molecules, basically the air column here will get the energy from this vibrator and they all will start vibrating, right. Suppose if the frequency of this tuning fork and the frequency of these particles inside here, if that becomes equals, when that becomes equals, right, we will get a standing wave like this. We will get a standing wave like this, right. Now, the question is, how do we make them equal? The frequency here is proportionate to 1 over L. L is this length. That means this frequency is inversely proportionate to length. So, let us say I am using a tuning fork with 512 hertz, let us say. Then what I should do is, to get the standing wave here, for the resonance to happen, I need to adjust this length and bring the frequency of this resonance tube also to 512 hertz such that the resonance can take place. Understand? So, now the question arises, how do we adjust the length of a resonance tube which has one side closed? We have a simple setup for that. What is the setup? We will take a long jar, right, we will take a jar and we will fill this with water. We will fill this with water, fill it with water. This is not the resonance tube, this is just a jar filled with water. Then what you do, take another tube, a smaller tube, and keep it here. Now, if you look at this part of the tube, see, this part of the tube will act like a resonance tube with one side closed. Why? One side closed means here you have water. So, this end is closed, the other end is open. So, you can take the tuning fork, vibrate it and keep it here. Keep it here. And how do we change the length? You just raise this tube, water level wouldn't change. So, when you raise the tube, the length of air column that is going to vibrate will increase. So, L will increase. When L increases, F will decrease. At some point, F will become equal to the frequency of the tuning fork. First time when that happens, that is fundamental note. Keep increasing after that also. You know, this is fundamental note. This is fundamental. Fundamental resonance. After this point also, if you keep increasing, what will happen? You know, at this point, L is equal to pi lambda by 4. If you keep increasing the height, if you keep raising it further, at some other point, you will have the wave shape like this, where you have two nodes, node 1, node 2. Why is it a node here? Because the particles here cannot vibrate, it's a closed end. They can't vibrate. Therefore, it is a node. right? This part has to be anyway antinode because it's free to move. Since the length is small, right, you get like this. This is what we call first overtone. First overtone. After the fundamental note, still if you keep increasing the length, after some more length, you will get a shape like this. So at this point, how do we know this happens? How do we know resonance happen? You can hear a loud sound, right? When these particles vibrate, at the point of resonance, they are all going to vibrate with a bigger amplitude. Then there will be a louder sound you can hear from the tube, which implies resonance. So this is where you will hear louder sound. And at this point also, you must be able to hear the louder sound, but understand, if I say this is the intensity I note, intensity of sound, I note, and if I say this is I1, first overtone, the intensity of sound, the loudness of the sound that you hear is I1, I note will be bigger than I1, because a smaller column is getting all the energy. So the amplitude will be much bigger. So you will hear a much louder sound. Here what happens, a very long air column is going to get the energy from this tuning fork. Both same tuning fork, but here the energy is going to be distributed for more molecules, right? Therefore, the amplitude they get even at the resonance point is less, right? Compared to the normal situation, resonance will have anyway more sound, louder sound. I am comparing two resonance points. Fundamental note resonance, first overtone resonance. First overtone, the intensity of sound will be less, right? Okay. So you can similarly, if you keep rising it, you can find the second overtone, third overtone also. But understand, the intensity of sound reduces when it goes to second overtone, third overtone. Sometimes you may not be able to observe it. You may not be able to hear that sound because the intensity drops, right? How can we say the length here? This time we have, say this is lambda by 4, another lambda by 4. So this L is going to be, this time, if this is L1, this is L2, L2 will be equal to 3 lambda by 4. And there is one more thing about the end correction. What is the end correction? When the open end is like this, we usually draw it like this, right? Sometimes the antinode can be a little bit outside the tube as well, because the particles are free to move, right? So antinode can be a little bit outside the tube as well. Then what happens? See, this is what you measure as L. There is some correction at the end, we call it end correction. Both together, L plus E is what is going to be lambda by 4. Similarly, in the other case, there will be an E here. So L2 plus E will be equal to 3 lambda by 4. That is if you consider the end correction also. So here we are going to consider end correction. That means that's the formula we will take. Then we know the frequency also. Why? Frequency is going to be the same frequency of the tuning fork, because when the resonance happens, frequency of the source, that is tuning fork, and frequency of the air column must be equal. That's how the resonance takes place. So we know the lambda, we know frequency. Then I can write formula like this. Look at this. From the first one I can say V equals F lambda. F lambda is going to be 4 L1 plus E, right? From this I can say L1 plus E is V by 4F. Similarly, when you substitute the second set of readings, V equals F. This time for lambda you have 4 by 3 L2 plus E. From this you get L2 plus E equals 3V over 4F. 1, 2. From these two we can solve and find V as well as E. How? 2 minus 1 will give you E cancelled, L2 minus L1 on this side. On the other side, if you take 4F common base, 3V, V, 2V. So 2, V will be 2F into L2 minus L1. L2 minus L1. L1 is the length of the tube. when when the fundamental note, first time you hear the resonance. L2 is the length of the tube when you hear the louder noise second time. That's first overtone we say. You want to find E, then you have to cancel V. But we will do first one into 3 minus second one. Then you will have 3L1 minus L2. This is going to be 3E minus E, that is 2E. Other side is 0. So E will be half. This goes to the other side as L2 minus 3L1. L2 minus 3L1. Right? So this is how we find the end correction. This is how we find the velocity. Do you understand the concept? Right. Let's see now. Materials and apparatus required for this: a tube of diameter about 2.5 centimeter and length about 50 centimeter. That's going to be the resonance tube. A tuning fork of known frequency. Make sure it's a known frequency. Known frequency. A meter ruler to measure the lengths. A tall jar and a stand. A tall jar and a stand. A jar is to fill water. Stand is to hold this tuning of, not the tuning fork, the resonance tube. Theory I already have explained it to you. This is how the setup is going to look like. A closed tube when resonating at the fundamental, let lambda be the wavelength of the wave, L the resonating length of the tube, and E the end correction of the tube, then lambda by 4 is equal to L1 plus E. From this we can say V equals 4F L1 plus E. I have shown this how we get this. Similarly, when it is the first overtone, you get like this. Solving those two, we get this. I explained you how to get this. Yes? Look at the methodology now. Immerse the tube in the water containing in the jar and fix it to the stand as shown in the figure. Arrange for a short length of air column in the tube. They asked this in the exam. Why do we have to start with a very short column of the air at the beginning? Because when you start from almost zero length and slowly increase, then only you can understand or you can find out the fundamental note. If you start somewhere from the middle and when you go up, if you see a resonance, how do you know that is fundamental note? That can be first overtone as well, right? That can be first overtone as well. So, to confirm that what you are getting first is fundamental note, you have to start from almost zero length of air column. Hold the vibrating tuning fork just above the upper end of the tube and raise the tube along the fork until an intense sound is heard, a louder sound, for the first time, indicating fundamental resonance. Using the meter ruler, measure the length L1 of air column. Hold the vibrating tuning fork again above the tube and raise it further to obtain the next state of resonance. That will be the first overtone. Measure the relevant length L2 of the air column and enter these readings. Right? So, we are going to get L1, we are going to get L2, and then we put it in the calculations. We can find the velocity as well as E. Clear? This is what we are going to do. Right? Come, let's see the experiment and see what readings we get. The apparatus required for this experiment. You can see this is a pipe, a plastic pipe we are using. This is filled with water. The water level is up to here. You can see that up to here we have water. Then we have another pipe which is actually both end opened, another pipe with smaller diameter. So, how do we make the resonance tube with one side closed? We will take this pipe, So, you can see it is open both sides, it is open here, it is open on the other side as well, right. Now, what we will do? We will be immersing it inside like this. So, what will happen once you immerse this inside the water? Up to here we have water, up to here. So, if you look at the tube or the pipe that is inside, the smaller diameter one, you have a column of air which is open at this end, a column of air which is open at this end and which is closed at this end, because we have water up to here. So, this length of air column is open here and closed there. So, that makes a resonance tube for us, one side closed resonance tube. If I want to adjust the length of this resonance tube, I can just increase it. See, when I raise it, now the length of resonance tube, the air column's length has increased. I raise it further, it further increases. Right, so this is how we make one side closed resonance tube which has adjustable length. Right, so that's how we make the resonance tube, leaving it there. We have a tuning fork. We have taken the highest frequency tuning fork because you know when f increases, lambda will reduce. So to keep the lambda short, we have taken the highest frequency tuning fork. This is of 512 hertz. This is of 512 hertz. Right? So that's 512 hertz tuning fork we are using. And we are using a hammer with rubber head because to make this tuning fork vibrate, to vibrate the tuning fork, we usually use rubber surfaces, soft surfaces, so that it doesn't damage the tuning fork. And we are using a meter ruler to measure the length of resonance tube when the resonance takes place. Additionally, we are using a stand to fix the meter ruler. We are using a stand. This is all required as apparatus to do this very simple experiment. Right? Let me show you how we are going to fix the meter ruler. Fix it inside the tube with water. Make sure you fix it vertically. Right. So see what we are going to do, the steps will be like this. I'll take this tuning fork, I'll make it vibrate, I'm going to keep it close to the end of this tube. I'll keep it very close to this. And while keeping it vibrated very close to this tube, I have to listen to the sound. So I have to keep my ear very close to this tube, resonance tube, and I have to increase the length of it little by little. So you must understand one thing there, when we are starting this experiment, we will keep this length as close as possible. Not actually required to keep it as close as possible, because since we know in theory we studied the speed of sound in air is 320 meter per second. So approximately if you calculate that, the answer for lambda by 4 has to be more than 10 centimeter for sure. We get around 13, 14, 15, around that range we will be getting it. So you don't have to start from very low centimeters, right, very low length of the resonance tube. Maybe you can start with like 8 centimeter. That means from the water level, the top of the resonance tube can be around like 8 centimeter, 10 centimeter length. You can start from there. From there, okay, so let me say now at water level somewhere around 44 centimeter it is there, right? Then I'll keep it somewhere around 54. That means around 10 centimeter. I'll vibrate this, keep it here. I have to listen to the sound very carefully. So you have to make sure you are doing this experiment in a very calm, quiet environment. If your environment is noisy, you will not be able to hear the sound clearly. The point where the resonance happened cannot be identified precisely. So make sure your environment is quiet. Right? Usually when we do this in the school labs, if the students make noise, if the students are talking around, you will not be able to hear, you will not be able to listen to the resonance precisely. So make sure it's a quiet environment. But here what I'm going to do, when I start doing this, I'll fix a microphone here. So when I fix a microphone, you will be able to hear the sound very clearly. Even though I can keep my ear here and listen to the sound, for you to listen to the sound, I'll keep a microphone here. So when I'm doing the experiment, since microphone is there, I will not be keeping my ear here. Instead, the microphone will absorb all the sound. Then I can identify the fundamental note as well as first overtone very clearly. Okay, right. So let's see now, we'll just do and see where we are getting it. Yes, I can hear the resonance. I can hear at some point the sound maximizes, but you won't be able to listen to that now. So to facilitate you to hear that sound clearly, let me fix a microphone and redo the process now. Students, you can see, as I mentioned, I have fixed the microphone here. You can see there's a microphone here. So you can hear all the sound when I increase the length of it. You can see the water level now is at 43, around 43 it is there approximately, right? Now what I'm going to do, I'm keeping it close to 51, 52 centimeter, that means around 7, 8 centimeter. Since we know the calculations, we already know in advance the answer has to be above 10 centimeter. That's why I'm starting at around 51, 52 centimeters. Let me vibrate the tuning fork. Slowly increase it. Somewhere at this point I hear the resonance. I'll show you again. Look at this. You can hear that once more. So that's the point where we get maximum sound. You can hear that. You can hear that this is the point where we hear the maximum sound. Let me measure the length. This is at 57 centimeter. You can see this is at 57. Let me check the water level. Water level is at 43 centimeters. You have to make sure every time you adjust the length, water level also will differ. Do you know why? The plastic pipe, when it is immersed into the water, it displaces some amount of water. When you raise it up, the amount of displaced water is going to be less. So the height will differ every time you adjust the height of it, right? So when it is at 57, I get the first resonance. That must be the fundamental note. When this is at 57, the height of water is at 43 centimeters, 43. So 57, 43, we get 14 centimeter length when the first resonance happens. So approximately lambda by 4 has to be 14 centimeters. But there can be some end correction, you know that, some end correction. To find the end correction also, what am I going to do? I am going to keep increasing this height to find where the first overtone takes place. That means the second resonance instance. That is where the first overtone happens. Let's increase. Now this has come 14 centimeter. You must know approximately 3 times of that, because this is lambda by 4. The next resonance is going to be at 3 lambda by 4. So you know approximately by 3 times of this length of air column, you must be able to hear the next one. So usually when you do the experiment in the laboratory, you don't necessarily have to go from this point. Approximately around twice or 2.5 times of this length, you can increase the length of air column, and then you can slowly observe it. Anyway, for you, I'll do from this point itself. Look at this. We don't hear any sound. Usually we have to keep the ear here and do it, so you must keep it at a level where you can, keep your ear and listen to that. But since I have a mic, I have kept it above me. Also, when you're observing the readings must be at your eye level. You can't keep a reading here. But for you all, we are going to keep the camera at that level and show it. Therefore, it's not a problem. But if you are doing it at lab, make sure when you are getting the readings, your eye level is at the reading level itself. Otherwise, there can be error in the readings. Still no. Still no. Not yet. Somewhere around this point we hear the sound. Let me do that again. Yes. This is the point where we hear the second resonance. You must understand, when we hear the second resonance, let me take the readings now. You can see the reading here. This is at 84 centimeters. 84 centimeters. When it is at 84, the water level inside the water pipe is at 82 centimeter, right? 82. So 84 here, 82 here, the difference is 42 centimeters. 84, 42, difference is 42, which is expected because 14 centimeter, thrice of that, approximately 42 centimeter it has to be. So we get approximately thrice of the length that we have got already, right? When we get the second instance of resonance, that means first overtone when we get, the level of sound that you hear might not be as intense as the first case. Because when the fundamental note takes place, that is where you get high intense of note. That is where highest energy is transferred and a small length of air is going to vibrate. Small length of air column is going to vibrate. So the vibration energy will be high. You will hear high intense noise or intense sound. When you go to the first overtone, that means the second instance of resonance, the sound you hear, there will be a peak. The intensity of sound will go to a peak, but at that peak, compared to the peak sound you heard in the first instance, it will be less. So you have to observe it, you have to keep the environment very quiet and carefully you have to observe it to find out where exactly you are getting the second instance of resonance. So here we have got the first one at 14 centimeter of air column length, second one we have got at 42 centimeters, 42 centimeters. But there can be reading errors. Do you know why? Here the maximum difference or the minimum difference we can measure is 0.5 centimeters. Right, you can see 60, 65, 60, 60.5, 61. Again see 60, 60.5, 61. So 0.5 only we can measure. Anything in between 0.5 we cannot measure. That's why I said approximately 14 centimeter and 42 centimeter we are getting. Right? The frequency I used is 512 hertz. Frequency I used is 512 hertz. So with these two, now let's do the calculations and find out the end correction if we have any. Also the velocity of sound in the air we are going to calculate. Students, you can see the readings we have got here. L1 was 14 centimeter, L2 was 42 centimeter, frequency is 512 hertz. So V equals F lambda. First case lambda is going to be 4L plus E. So we will get V over 4F equals L1 plus E. I explained this earlier also. Then you get 3V over 4F L2 plus E. 1, 2. 2 minus 1. You get V will be equal to 2F L2 minus L1. Let's apply this to 512 L2 minus L1. 42 minus 14 is 28. But that's in centimeters, 10 to the power minus 2. So this is 1024 into 28. 28. 32, 3, 19, 8. 2048. 2, 7, 6, 8, 2. 28, 6, 7, 2. 10 to the power minus 2, 286.72. Actually, the velocity we study is around 340. So this might be because of any errors in the experiment. Also, like the frequency we use the tuning fork, even though it is denoted as 512 hertz. When you keep using it for a longer time, the frequency might differ, right? So the actual frequency might have been different from this, right? So due to reasons like that, we get slightly or significantly different answer for V. And the end correction we can get, end correction how do we do? 2 into 3, no, 1 into 3 minus 2. I will say 2 minus 1 into 3. Then from that you will get E equals 2 half L2 minus 3L1. Half L2 is 42. 14 into 3, that is also 42. So we get 0 end correction here. We get 0 end correction here. Right? So that's how the calculations will look like. Not at all complicated. Very simple, straightforward experiment it is. Now let's see how this has been tested in the past exam questions. Let's see the past papers from this experiment. This is from 2002 paper. You are given a uniform glass tube with both ends open, a tuning fork with frequency f 512 Hz and a jar with water. An experimental arrangement has to be made to find the velocity of sound in air using resonance. Draw a diagram to show the experimental arrangement. Simple. We will draw the jar and then the resonance tube. And then water. You need the meter scale also. Let's draw the meter scale. How do we arrange it? With the help of the stand. Right. Simply that's the arrangement. This is the meter ruler. You can show the scales if you want. A simple diagram with the arrangement. Yes. State the correct procedure that you would follow in order to obtain the resonance of the air column. Right. We know the steps. That's what we have. That's what we have done. Let's write down. Keep the resonance tube immersed in water with a small air column outside the water, right? Then vibrate the tuning fork and keep it near the open end of the tube. Slowly raise the tube to increase the length of air column. Until a loud sound is heard. Right. At this instance, the air column resonates with the tuning fork. Simple. Next, what are the two readings you would take to find the length of air column? You know the two readings we get, the readings at water level, reading at the upper end of the tube. One is water level. The other one upper end of resonance tube. The height of water level, let's say the height of water level and the upper end of the resonance tube. Write down a common formula for resonance length L in terms of wavelength lambda of sound and an integer n. Look at this. When we did it for like first resonance that we hear, that is a fundamental note. So imagine when we do the fundamental, when we get the fundamental resonance, what we get is lambda equals, or lambda by 4 is equal L. For the first overtone, we get 3 lambda by 4 is equal to L. Second overtone will be 5 lambda by 4 equals L. Right? This is just for you to understand. Huh? So what we can say, the L equals n lambda by 4, where n takes values 1, 3, 5, likewise all the odd numbers it takes. Correct? You know why it is so? Lambda by 4 is because you get only this much. In the first overtone you get this much. So 3 lambda by 4. Right? In the second overtone is going to be like this. So that's going to be 5 lambda by 4. Because of this, the number for n can be 1, 3, 5. That's what they asked. Write a formula for lambda. So we'll change it. Lambda equals 4L by n. Lambda equals 4L by n. Write a suitable formula in I, V, F and N to find the speed of sound in air using graphical method. V equals F lambda. F lambda is 4L by n. 4L by n. From this we can say L equals V E over 4F into n. Y mx. Y equals mx. That means for the fundamental overtone, n is going to be 1. Then for the first overtone, n is going to be 3. Second overtone, n is going to be 5. Each time you measure L and draw the graph, you will get like this. They did not mention anything about the n correction, so don't take it here. Otherwise, it would have been L plus E here. The first two resonances lengths in this experiment were 15 centimeter, 48 centimeter. Draw the wave pattern for the above two in the following figures. Right, first one, fundamental overtone. Fundamental note is like this. See, if I divide it into 3, correct? Yeah. That's how it will be. That's 48 centimeter. Shouldn't go out, it must be inside. What is the type of wave in tube of at resonance state? Is it travelling wave or standing wave? It's standing wave. It's standing wave. Very easy question. See how straightforward basic questions they ask. That's standing wave. Rewrite the formula in part E including n correction E. So what will happen? This formula L will become L plus E also. So that E will go to the other side as minus E. So it's going to be L equals V by 4F into N minus E it's going to be. Because L plus E would have been here, it goes to the other side. So now you have Y equals mx minus C. Find the speed of sound in air using the values given in F. The values you have got are 15 and 48. 15 and 48. So let's say when n is equal to 1, L is V by 4F minus E, right? N is equal to 2, or L is given 15. N is equal to 3V by 4F minus E, capital E we have used, is 48. So you subtract it, you get 2 minus 1, you will get V equals 2F into, because here you get 2V over 4F, that's 2F, 48 minus 15 is 33. Do we know the frequency? 512 hertz, 512 hertz. So, you can use 2 512 into 33. This is 1024. Oh wait, 33 is in centimeters. Okay, we'll convert that to meter. 3066 3066 66633. So, you get 33666 centimeter per second, which will be 336.66 meter per second. Correct? They are asking you to find the velocity or end correction. Rewrite the formula is what they asked. In the next part only they asked you to calculate the value speed of sound. So, this working you will write there. You get 336.66. 2013. A similar question has come in 2013 paper also. Have a look at this 2013. A glass tube, a measuring cylinder with water, a meter ruler and a tuning fork of frequency 512 Hz are provided to determine the speed of sound V in air and the end correction of the tube E. When the glass tube is completely immersed in water and then raised gradually, resonances can be heard when the heights of the tube above the water level are 0.169 meter, 0.169 meter and 0.509 meter. So, that must be the fundamental note, this must be the first note. Draw the waveform for the resonance heard for the first time in figure 1a. It's going to be like this. Right. Draw the tube, water level and the waveform for the resonance heard for the second time in figure 1b. Okay. So, figure 1b, what should happen? If this is lambda by 4, here we have 3 lambda by 4, right? So, look at this. Water level must be more or less same. No big difference in the water level. Right? But the tube has to be almost 3 times of this length. 1, 2, 3. 3 times of this length you have to do. Almost. Better I would say you take your ruler, measure how many centimeters it is. Suppose if it is 3 centimeter, draw that as 9 centimeter to be on the safe side, because 3 lambda above 4 it's going to be. Some students have drawn it at the same length itself. They were not given marks. Right, within the same length they have shown like 3 lambda by 4, 3/4 of the wave, which was not given marks because the length has to be higher than right. That's how it's going to be. Correct? Clearly mark the height L2 which you would measure in figure 1b. L2 will be this length, right? Right. That's what you are going to measure as L2. L2 is marked. Fourth one. B, first one. Obtain an expression for the speed of sound V in terms of E, F, L2 by considering the resonance heard for the first time. Right. B, E, F, L, L1. L1. Must be L1. Yeah. Because first time when you hear the resonance, it's L1. So, we can say L1 plus E is lambda by 4. Then you can say V equals F lambda, F 4 L1 plus E. So, V is 4F L1 plus E. Next, write down the form expression for the speed using the second time. That means 3 lambda by 4. This time you are going to say L2 plus E. I have explained this before the experiment also. Straightforward questions. For lambda, you will have 4 by 3, isn't it? L2 plus E. V equals 4F by 3 L2 plus E. Second one. Using the result obtained in B1 and B2 above, obtain an expression for V in terms of L1, L2 and F. So, what we are going to do, This is 4f by 3. This is 4f. So, we will multiply second one by 3 and subtract the first one. Then that 4f by 3 E will be cancelled, right. See, I'll write it, V equals 4f L1 plus E is there. V equals 4f by 3 L2 plus E is there. This is what we have already written for the previous parts. So, we will say 1 into 3, no, 2 into 3. When you multiply by 3, this 3 is going to get cancelled, minus first one. So, you will have 3v minus v, 2v. Here, if you take 4f common, here you have L2, here you have L1. E will be cancelled, E and E will be cancelled. When you multiply this by 3, you are going to have 3v equals 4f into L2 plus E. 4f common, E and E will be cancelled, L2 minus L1 remains. So, V equals 2f, nothing much, nothing new, we have done this several times. Next, hence calculate V and E. Hence calculate V and E. We know the L2 and L1. F was 512 hertz. Have they given the lengths? 0.109, 169 and 509. 169 and 509. V 2 512.509 minus 0.169. That's 1024 into, this is going to be 0.34. 1024, 34. This is 96, 4. Then 3072, 61843. You get 348.16 meter per second. That's for V you are getting. Here find E as well. So, maybe you can apply in first one, or else we can find E directly. How? We will eliminate V. How? You can equate these two. 4f L1 plus E, 4f by 3 L2 plus E are equal, because both are V. 4f cancelled, right. 3L1 plus 3E, bring it here, E will be equal to half L2 minus 3L1. The formula we already studied, but let's just prove it and use it. L2 509. If it is 170, it would have been 510. So, it's 3 less, 507. Here 509. So, you will have half into 0.002. 0.001 meter, which is 0.1 centimeter. The end correction is 0.1 centimeter. Clear? Right. A student suggested to use a graphical method to determine V and E, taking measurements of several resonance states of the tube with the tuning fork. Write down 2 difficulties of different nature in performing such an experiment to obtain sufficient number of measurements. First problem, when you get second overtone, third overtone, length of tube has to be much bigger. Why? Lambda by 4 is going to be there, the first length. Then 3L by 4, 3 lambda by 4. Then 5 lambda by 4. So, suppose if the first reading is 16 centimeter, 17 centimeter. Second reading is going to be 51 centimeter. Third reading is going to be 17 into 5, which is 85 centimeter. So, you need a long tube, right. So, that is one problem. Practically it's difficult to do this experiment because you have to vibrate it, keep it on the top, and you have to move both. So, probably you need a ladder to climb and do this experiment, which will be difficult. Second thing, the intensity of sound you hear will be less, right. First fundamental note, you hear high intensity of sound. First overtone, it is less than the first resonance. Second resonance, it was less. So, when you go to the third resonance, fourth resonance instances, the intensity of sound, even though it's a loud sound compared to the near points, that loud sound itself will be not enough for you to listen to. You won't be able to hear that, right? So, let us write the reasons here. First one, the intensity of sound for second, third overtones will be very low and cannot be heard. The resonance tube or the length of resonance tube has to be, or they can say the resonance tube has to be, the resonance tube has to be much taller or much longer to observe second, third overtones. Understand? These are the main practical issues you have in getting more overtones heard. Understand? So, can you see the questions we get are very fundamental, right? Waves and oscillations questions, the questions you get are quite fundamental. You don't have any complications here, right? Now, this is one past paper. Now, we will take another one, a most recent one, and see how this has been tested. 2016 paper it is. Figure shows an alternative apparatus to find the speed of sound in air using the resonance tube with one end closed. The principle of this apparatus, let us have a look at the apparatus. Alright, okay. So, what they are going to do to have the length of air column to be changed, they have a different setup here. They have a different setup. So, let us see what it says. The principle of this apparatus is similar to the principle of the apparatus normally used in the school laboratory. The resonance tube in this apparatus is a glass tube with a calibrated scale. The water level in the resonance tube is raised and lowered by raising and lowering of water reservoir X, which is connected to the resonance tube with a flexible rubber tube. Now, look at this. When you raise this up, accordingly this also will have to go up. So, when you raise this, it goes up, and then the air column becomes shorter, correct? Is that what they say? The water level in the resonance tube is raised and lowered by raising and lowering a water reservoir X, which is connected to the yes. So, by if you lower it, accordingly this also has to get adjusted, right? So, what type of wave is formed inside the tube at resonance, right? It is a standing wave. We know that it is a standing wave. Standing wave. You are given a tuning fork of known frequency f and asked to obtain the resonant lengths L note and L1 corresponding to the fundamental note and the first overtone respectively. Draw the wave pattern for the two modes of vibrations and mark the lengths L note, L1, end correction E, notes and antinotes. You are expected to draw the tube for the first overtone. First overtone, okay. Draw the wave pattern for the two modes of vibrations and mark the lengths L note, okay. Let me draw it like this, or we will draw it vertically. Right. Let us mark this as L note and this is what is E. This is the node, this is the antinode. Now, to draw the first overtone, I have to draw the length thrice as this much. Thrice as this much. Right. L node L1, L1 E nodes antinodes. Next one, next. If lambda is the wavelength corresponding to the fundamental note, write down an expression for lambda in terms of L node and E. Easy, easy. Lambda by 4 equals L node plus E. So, lambda equals 4 L node plus E. Lambda equals 4 L node plus E. Write down a similar expression for the wavelength corresponding to the first overtone. 3 lambda by 4 equals L1 plus E. Lambda is 4 by 3 L1 plus E. If V is the speed of sound in air, derive an expression for V in terms of the known and measured quantities. V equals F lambda for fundamental note, V equals F into lambda. Lambda is going to be fundamental note is going to be 4 L node plus E. 4 L node plus E. First overtone, F into 4 by 3 L1 plus E. First one, second one. We will say we are going to do this. Let's say 2 into 3 or yes, 2 into 3 minus first one. 3V minus V, 2V, 4F common, L1 minus L naught. So, V is 2F into L1 minus L naught. Right? The usual equation, there is nothing new in that. Next. Before taking the measurement for L naught, the water level in the resonance tube has to be raised up to the top. Explain the reason for this. So, why do we start from very small air column? Because first time when you hear the resonance, that has to be the fundamental note. If you start somewhere in the middle, then if you hear the resonance, you wouldn't know whether it is fundamental note or a first overtone, right? So, let us say to ensure that the first resonance is of fundamental note, First resonance is of fundamental note. Write down two major differences in experimental procedure when using the apparatus given in question compared to the method adapted when using apparatus generally available in school laboratory. So, school laboratory, what do we do and what is the differences between these two? Let me draw the usual arrangement and show it to you. This is our usual arrangement and we keep a meter ruler here. So, first difference you can see, it's like they give two pictures and say spot 6 differences, something like that. So, first difference you can see, here we use a separate meter ruler, here we have a glass tube with the scale itself. So, you don't need the meter ruler. Point number 1, difference number 1. Difference number 2, here if you want to increase the air column's length, you have to raise the tube. Here the tube is fixed. right? You are raising the water level. By raising this or lowering this, you are raising the water level, correct? That's all the differences are, right? The two differences, first one, you don't have to use a meter ruler here. Second one, the air column adjustment, length of air column is adjusted not by raising the tube, but instead raising the water level. So that's a basic question asking you to find the differences. First we can say no need of meter ruler. No need of meter ruler. Second one, in usual arrangement, water level is fixed and tube is moved, tube is raised. In this, tube is fixed and water level is raised. Water level is raised. Okay. The last part of it. At room temperature 28 degree, when 512 Hz tuning fork is used, the corresponding lengths of the resonance for fundamental note and the first overtone are found to be 15.5 cm and 50.5 cm respectively. Calculate the speed of sound in air at room temperature. Simple. We already have the formula. V equals 2F L1 minus L0. We have proven that in a previous part. 2 512 L1 minus L0, 50.5, 15.5, 35. 1024 into 35. 1024 into 35. 125. 3072. 04853. 358.4. 35840 centimeter per second, which is 358.4 meter per second. Clear? Right. So that's all the past paper questions regarding this experiment. I have done 3 past paper questions on this. Hope you understood that. Practice that couple of times. Waves and oscillations, the questions you get are quite basic questions, nothing much complicated in that. You should be able to answer that comfortably. Right? Finishing that in the next session, let's meet up with another experiment.